Good afternoon, students. This is Arvind, Assistant Professor, Department of Degree, DBS Kavali. So, in the previous session, I discussed about some thyristor-based converter operations like rectifier operation and inverter operation. And now, in this class, I am going to discuss the remaining operations, that is valve voltage, commutation failures, and AC current harmonics and DC voltage harmonics, like that. Okay. So first I will discuss the thyristor-based converter operation in the valve voltage. So here I will show the diagram. It shows the valve voltage. For example, I am taking the valve number 5, that is diode. Sorry, thyristor 5, not diode. It is a thyristor in this one. So valve means thyristor. The thyristor number is 5 during the inverter operation. So at that diagram, the upper waveforms shows the AC voltage, valve sequence, and the voltages during commutations. So as explained before, the commutations are enabled by short circuits between phases. Okay, during these short circuits, the voltage of the two short circuited AC phases follow the mean of the respective two phases. So actually, it is a three-phase system. So during these short circuits, the voltage of the two short circuited AC phases follow the mean of the respective two phases. So diagram for valve 5, that is for the thyristor 5, valve 5 voltage shows that during conduction period of 120 degrees plus gamma, the voltage is 0, and at the end of commutation from valve 5 to valve 1, the voltage jumps to a negative value corresponding to the voltage VCA. So this is the diagram I am discussing. So this diagram gives the voltage across a valve in a thyristor converter. That too, here I am considering the valve number 5 only. Okay, first diagram gives the converter operation as an inverter. First diagram gives the converter operation as an inverter, and second diagram gives the voltage across valve number 5. Okay, so this is the first and this is the second. So the first diagram gives the converter operation as an inverter, and B diagram gives the voltage across valve 5. Okay. So, as mentioned before, the duration of this negative voltage needs to be sufficient for valve 5 to recover before the voltage goes positive. So, as the valve voltage follows voltage VCA, so it is destroyed by change in the voltage VCA during short circuit of phases B and C for commutation from valve 6 to valve 2. So following that, it is again distorted by the change in voltage VCA during commutation from valve 1 to valve 3. So however, at the completion of this commutation, the valve voltage follows the voltage VCB, which is later distorted by commutation from valve 2 to valve 4. So the cycle is complete when the valve 5 turns on again. Why? Because here I am taking only one valve, single valve. That's why if the cycle is complete when the valve 5 turns on again. That means one cycle is completed when it reaches to the value, and again the valve 5 is turns on again. Okay. Next, thus the voltage across valve number 5 connected to phase C follows the voltage waveforms VCA and VEB. Okay. So similarly, the voltage across valve 2. So actually in this one I am taking only the valve number 5. Suppose if you take the voltage across valve 2, the other valve connected to phase C follows the voltage waveforms, that is VAC and VBC, and so on. Like that it will continue. It continues. So during the inverter operation, the valve voltage is positive much of the time, and obviously during rectifier operation it will be negative much of the time. So during the rectifier operation it will be negative, and during the inverter operation the valve voltage is positive. and given the circuit inductances and capacitances, there will be a voltage overshoot at each voltage jump. There will be a voltage overshoot at each voltage jump, resulting in higher valve voltage when the overshoot is during the peak of the valve voltage. Okay, so it is therefore necessary to provide RC damping circuits, that is inductances and capacitances and resistance circuits across the valve devices. Valve devices is nothing but thyristors. Okay, next that is for the valve voltage concept of the thyristor-based converter. And next coming to the commutation failures. Coming to commutation failures. So it was mentioned earlier that a safe minimum angle of advance beta is needed in order to allow successful commutation of current, that is angle gamma, and for the outgoing valve to fully recover, that is gamma greater than, delta greater than delta naught, before the voltage across it reverses and becomes positive. Okay, and otherwise the outgoing valve will commutate the current back and lead to a fault known as commutation failure. So actually this point is also discussed in the previous class, commutation failure. Okay, commutation failure means the outgoing valve will commutate the current back and lead to a fault known as commutation failure. So on one hand, it is desirable to minimize the angle beta when it is necessary to maximize the inverter output voltage. So on the other hand, allowance has to be made for current rise and or reduction of the AC system voltage just before and during the commutation process. Next, some allowance has to be made for reasonable events. So some allowance has to be made for reasonable events, and then it has to be accepted that some commutation failures will still occur on the some statistical basis and provide for a safe ride through. Okay, so referring to the diagram of 4.11, I will show the diagram later. So referring to the diagram, the time instant t1 is the point where valve 1 and 2 are conducting, valve 3 turns on, and commutation from valve 1 to valve 3 is expected to take place. Okay, suppose the commutation fails to complete by point T2, the point of voltage crossing. So the commutation will reverse as shown, and valve 1 together with valve 2 will continue to carry the DC current. Okay, consequently, the DC voltage continues to fall as per voltage VCA. So then at point T3, valve 4 turns on to take over the current from valve 2, at which time VCA is short circuited and DC voltage falls to 0. Like that the operation continues from T1 to T2, T3, T4, T5, T6, like that the operation will continue. Okay. So this is the diagrammatic representation of the this one. So actually this is also shown in the inverter operation also. Same diagram I have been taken for the inverter operation. Okay. So based on inverter operation, the commutation failure and valve voltages all are coming. Okay. So this is the diagrammatic representation for the commutation failures. And next coming to this one. So this is the waveforms we are telling. So this waveform is for the phase voltages. Okay, phase voltages, and this is for the one commutation failure, and this is for the two commutation failures. Actually, we will have two commutation failures. So one is single commutation failure, and another one is double commutation failure. So the second waveform gives the single commutation failure occurs. So second waveform, third last waveform gives the double commutation failure. Okay. So now assuming that the commutation from valve 2 to valve 4 is successful, the DC current is effectively bypassed through the phase leg of valves 1 and 4. So following that, valve 5 has no chance to take back the current because its voltage is reverse biased. Okay, the DC short circuit ends T4. The DC short circuit ends T4. So when valve 6 takes the current over from the valve 4 with the DC voltage going slightly negative first and the converter continues to function correctly. So this type of commutation failure is referred to as a single commutation failure. Okay. Next, so when a commutation failure occurs, the scenario is more likely to end with a single commutation failure, given that the DC inductor is large enough to limit the rate of rise of current and the protective means advance the turn on of the next valve with deflection of commutation failures. Okay. So again, there is no guarantee that the commutation of the next valve. So we don't know. Immediately after the commutation failure will be successful. So if the commutation failure occurs, so immediately after the commutation failure, it will be successful. Who knows? So in the example above, if the commutation from valve 2 to valve 4 also fails to complete, then the DC output voltage will go through a full AC cycle voltage V suffix A. So following that, if all else is well, the normal operation will continue. So otherwise, it is a failed operation. Okay. So in general, this problem is quite manageable in power systems as is evident from a large number of HVDC projects in the satisfactory operation. You have to take a large number of HVDC projects for a satisfactory operation. Okay, next. That is for the computation failure. And coming to the next one, that is AC current harmonics. So here I am neglecting the commutation angle. So for the AC current harmonics, I am neglecting the commutation angle. So the current is made up of 120-degree pulses. So I will show the diagram. If I show the diagram, you will understand that one. So analysis of AC current can be obtained by Fourier analysis and is given by In is equal to 2 root 3 by pi into Id of cos omega t minus 1 by 5 cos 5 omega t plus 1 by 7 cos 7 omega t minus 1 by 11 cos 11 omega t plus 1 by 13 cos 13 omega t and so on. Like that, the analysis of AC current will obtain from the Fourier analysis. So the harmonics are of the order of, so here the harmonics are of the order of 6k plus or minus 1. So where k is an integer. So the RMS value of any term in the above equation is given by In is equal to Id into root 6 by pi n pi, root 6 by n pi. So with n is equal to 1, the RMS value of the fundamental is given by I1 is equal to, that is for the fundamental, that's why I am taking I1. So I1 is equal to root 6 by pi into here n is equal to 1. That's why we have root 6 by pi into Id. Finally, we have the fundamental RMS value of the current is 0.78 Id. Okay. Next. So this is the waveform. So actually this gives the 6 pulse and 12 pulse current source converters. Okay. So first diagram gives the 6 pulse star to star connection. So star to star connection, circuit and current waveforms. Okay. So on the right side we have the circuit and on the left side we have the waveforms. And the second diagram gives the 6 pulse star delta circuit and current waveforms. And third circuit gives the, third one gives the 12 pulse circuit and current waveforms. So on the right side we have 12 pulse circuit and on the left side we have the current waveforms of that circuit. Okay. So here the ratio is for the first circuit, that is the 6 pulse star to star circuit, 1:1, and for the 6 pulse star to star delta circuit we have the ratio root 3:1, and for the 12 pulse circuit we have the ratio 2:1 and 2 root 3:1. Okay. So here the angle is changes. So assuming first one, that is 1:1 ratio of star to star transfer, star transformer. So if a delta star transformer with root 3:1 one ratio is adopted, the secondary voltages of this transformer would be displaced by 30 degrees with respect to the corresponding voltages in a star to star transformer. Okay, so here the line current will now be as shown in the figure B. So that is this one. So this one, diagram B. Okay. So the line current will now be shown as like that. So the analysis will show that the harmonics are defined by the same. That means except the harmonics of the 5th, 7th, 17th, 19th, 29th, etc. Orders are of opposite sign. Okay. So when two 6-pulse converters of equal capacity, one with star to star transformer of ratio 2:1 and the other with a delta star transformer of ratio 2√3:1 are connected together. That is the last diagram. See, okay, are connected together in either series or parallel. The resultant current is given by IN is equal to 2√3 by pi into ID of cos omega t 1 by 11 cos 11 omega t plus 1 by 13 cos 13 omega t minus 1 by 23 cos 23 omega t plus and so on we have. So next, assuming the 1:1 ratio, so I already discussed this one. So actually the equation represents the AC current of a 12-pulse converter and has a waveform as shown in the last diagram. Okay. Next, harmonics of the orders 5th, 7th, 17th and 19th which do not enter the AC system will circulate between the two 6-pulse converters. So the harmonics are of the order of 12k plus or minus 1. Here the harmonics are of the order of 12k plus or minus 1, where k is an integer. In fact, a 12-pulse converter will often have one with one primary and two secondaries. Okay, so it follows that one can have a 24 pulse converter by combining four 6-pulse converters. Four 6-pulse converter. So with 15 degrees phase shift obtained with phase shifting transformers. Okay, with phase shifting transformers. The equation above took no account of commutation angle. And next, so however, it is important to consider the commutation angle because the harmonics decrease considerably. So if this is considered, the current wave shape for analysis can be defined in three parts. So if that will consider the current wave shape for analysis defined in three parts. So that is IP is equal to ID of cos alpha minus cos omega t by cos alpha minus cos alpha plus gamma. So this is for alpha less than omega t less than alpha plus gamma. That is the angle is vary between alpha to alpha plus gamma. So at that time we have IQ is equal to ID. Okay, IQ is equal to ID. And for this is for alpha plus gamma less than omega t less than 2 pi by 3 plus alpha. So next IC is equal to ID minus IP is equal to ID minus ID of cos alpha minus cos omega t minus 2 pi by 3 by cos alpha minus cos alpha plus gamma. So this is for 2 pi by 3 plus alpha less than omega t less than 2 pi by 3 plus alpha plus gamma. So like that it is the current wave shape is divided into three parts. Okay. So this is the diagram. So here the current waveform is divided into three parts. Okay. One is for first I will tell that omega it varies from alpha to alpha plus gamma and next alpha plus gamma to 2 pi by 3 plus alpha and next 2 pi by 3 plus alpha to 2 pi by 3 plus alpha plus gamma. Like that the current waveform is varies with the angle. Okay, here we have alpha, beta, 2 pi by 3, IP, IQ, ID, IP, like that we have alpha plus gamma, 0, and alpha plus 2 pi by 3, alpha plus gamma plus 2 pi by 3, like that it continues. Okay, this is the DC current and voltage waveform definition for the harmonic analysis. And next, so based on the Fourier analysis of the waveform defined above, the figures 4.14 to 4. So actually we have the total 5 diagrams. So the 5 diagrams show curves of the harmonic current IN as percentage of the fundamental I. Okay. So I against the commutation angle gamma for different values of alpha or gamma for the 5th, 7th, 11th, 13th, 17th and 19th in order to convey the nature of these curves. So curves for specific values of the delay angle alpha and the margin angle delta are the same because delta is a mirror image of alpha. Mirror image of alpha. So it is seen from these curves that as gamma increases, the magnitude of harmonics decreases and with higher orders decreases more rapidly. So here each harmonic decreases to a minimum at an angle gamma is equal to 360 by n and then rises slightly thereafter. So it is worth nothing that for practical purposes gamma will likely be in the range of 15 to 30 degrees at full load. Okay. So I will show in the next total 5 diagrams. So these 5 diagrams have the curves of the harmonic current IN, okay, as percentage of the fundamental I against the commutation angle gamma for different values, okay. So obviously the voltage harmonics on the AC system side are a function of the AC system impedance for each harmonic current injected into the system by the converter. So this is the diagram, this is the first diagram. So it consists of the angle of overlap, that is gamma, and on the y-axis we have the percentage of fundamental, that is IN. So this diagram gives the variation of fifth harmonic. So here I am considering the fifth harmonic current in relation to a angle of delay gamma, to a angle of delay alpha or margin angle delta, because the margin angle and the delay angle is the same, and commutation angle gamma. So here I am taking the angle of overlap gamma in degrees, like from 0 to 40 degrees, 0 to 40 degrees, and the current values will taken as in percentages from 0 to 20. Okay. So here alpha angle is increasing, that means alpha is equal to 0, we have one curve, and alpha is equal to 20, we have one curve, and alpha is equal to 30, at alpha is equal to 30 we have one more curve, at alpha is equal to 40 we have one more, and alpha is equal to 60 we have one more. Like that we have we will form the current waveform. Okay. So this is the variation of fifth harmonic current in relation to the angle of delay and commutation angle gamma. Okay. Next, so this is the diagram. This also gives the variation of seventh harmonic current. So previous diagram shows the variation of fifth harmonic current in relation to the angle of delay and commutation angle gamma. So here I am taking variation of seventh harmonic current in relation to angle of delay alpha and commutation angle gamma. So this is the diagram. So here on the x-axis I am taking angle of overlap, that is gamma, in degrees from 0 to 40, and next I am taking the current in percentage, fundamental current in percentages. So here I am taking from 0 to 17%. So here the order of the harmonic is 7, that is n is equal to 7. So here at alpha is equal to 0 we have one curve, and alpha is equal to 10 we have one curve, and alpha is equal to 20, and alpha is equal to 30, alpha is equal to 40, and alpha is equal to 80. We have different curves we have for the variation of seventh harmonic. Okay. Next, so I am taking one more diagram, that is for variation of 11th harmonic. So up to now we seen 5th and 7th harmonic. Next, I am taking the variation of 11th harmonic. So here the order of the harmonic is 11, that is n is equal to 11. Here also I am taking the angle of overlap and the angle of delay, both in relation to the fundamental current IN. So same repeats the curve. So at alpha is equal to 10, we have one curve, alpha is equal to 20, we have one, alpha is equal to 30, we have alpha is equal to 40, we have one curve, and alpha is equal to 80 and alpha is equal to 0. We have different curves. And next, variation of 13th harmonic currents. Variation of 13th harmonic. So that means here the order of the harmonic is 13, n is equal to 13. So here also I am taking variation of 13th harmonic current in relation to angle of delay alpha and commutation angle gamma. So at alpha is equal to 0 we have one thing, and alpha is equal to 10 we have one thing, and alpha is equal to 20 we have one curve, at alpha is equal to 30 we have one curve, at alpha is equal to 40 we have one curve, at alpha is equal to 80 we have one curve, like that we have. And then again I am taking variation of 17th harmonic current in relation to angle of delay alpha and commutation angle gamma. So here the order of the harmonic is 70. Okay. So here also I am taking on the x-axis angle of overlap gamma and delay angle alpha and fundamental current In. So now we are varying the angle of delay from 0 to certain angle. So up to here I am taking 80 degrees, 0 to 80 degrees. So but angle of overlap is 0 to 40 only. So at that time the curve is shown like this. Okay. And coming to the last one, that is the variation of the 19th harmonic in relation to the gamma and alpha. So the waveform is like this. Okay. Okay, thank you for watching this video. And in the next class, I am going to discuss one more thing, that is DC voltage harmonics, and we have comparisons between current source converter and voltage source converters. We have. I will discuss those two concepts. After that, I close second chapter of this subject facts. Okay, thank you.